Lesson: Theoretical basis of model evaluation metrics. Understanding the theoretical basis of model evaluation metrics is crucial for AI professionals aiming to optimize performance. Evaluating models is not just about determining accuracy, it's about understanding the underlying principles that make one model more suitable for a particular application than another. This lesson delves into these principles, offering actionable insights and practical tools to enhance the proficiency of AI professionals. Model evaluation metrics are the benchmarks by which we assess the performance of machine learning models. The selection of appropriate metrics is paramount because it influences model selection, tuning, and deployment. A critical understanding of the theoretical basis of these metrics ensures that the selected models align with the problem's objectives and constraints. Various metrics exist, each providing unique insights into the model's performance. For binary classification problems, metrics such as accuracy, precision, recall, and F1 score are frequently used. Accuracy, though intuitive, can be misleading, especially in imbalanced datasets where the number of instances in one class significantly outweighs the other. For example, in a dataset where 95% of the cases belong to one class, a model predicting the majority class every time achieves 95% accuracy, yet fails to capture the minority class's significance, which might be critical for decision-making. Precision and recall become more meaningful in such scenarios. Precision measures the number of true positive predictions made by the model divided by the total number of positive predictions. Recall, on the other hand, measures the number of true positives divided by the number of actual positives. These metrics are often used in tandem to provide a more holistic view of the model's performance. The F1 score is the harmonic mean of precision and recall, effectively balancing the two. This metric is particularly useful when seeking a balance between precision and recall. For instance, in a spam detection system, high precision is crucial to ensure that legitimate emails are not flagged as spam, while recall ensures the system identifies as many spam emails as possible. For multi-class classification problems, metrics such as macro average and micro average precision, recall, and F1 score are employed. Macro averaging treats all classes equally, calculating the metric independently for each class and then averaging, whereas micro averaging aggregates the contributions of all classes to compute the average metric. This distinction is vital. Macro averaging is beneficial when classes are equally important, while micro averaging is preferable when class imbalance is present. Regression tasks employ different metrics such as mean absolute error, mean squared error, and root mean squared error. MSE gives more weight to larger errors, which can be advantageous when outliers are significant, but MAE is more robust to outliers as it treats all errors equally. RMSE, being in the same unit as the target variable, provides an interpretable measure of error magnitude. These metrics, when chosen appropriately, provide significant insights into model performance. In a housing price prediction model, for instance, RMSE might be preferred because it penalizes large errors more severely, which are often more costly in real-world applications. Beyond these traditional metrics, ROC AUC is a robust metric for evaluating binary classifiers. It measures a model's ability to distinguish between classes and is particularly useful in scenarios where the class distribution is imbalanced. AUC provides a single value metric that summarizes the trade-off between the true positive rate and false positive rate across different thresholds. A model with an AUC of 0.5 is no better than random guessing, while a model with an AUC closer to 1 indicates strong classification performance. Practical implementation of ROC AUC can be seen in medical diagnostics, where distinguishing between the presence and absence of a disease with high accuracy is crucial. Practical tools and frameworks, such as scikit-learn in Python, offer comprehensive suites for calculating these metrics efficiently. Scikit-learn's metrics module provides functions for computing accuracy, precision, recall, F1 score, and AUC, among others. Integrating these tools into the model evaluation process involves a few straightforward steps: importing the necessary module, fitting the model to the data, and using the appropriate function to compute the desired metric. Case study applications, such as evaluating a sentiment analysis model, illustrate the utility of these metrics. By applying precision, recall, and F1 score, one can determine the model's effectiveness in identifying positive and negative sentiments accurately, thereby optimizing performance. The theoretical understanding of these metrics is supported by statistical principles and probability theory. For example, the precision recall trade-off is rooted in the probabilistic distribution of predictions. Thresholds play a critical role in this trade-off, influencing the balance between precision and recall. Adjusting the threshold alters the classification boundary, thereby affecting the number of false positives and false negatives. This adjustment is particularly evident in cases where the costs of false positives and false negatives are asymmetrical, such as fraud detection systems, where false negatives are typically costlier than false positives. Furthermore, advanced techniques such as cross-validation are integral to the reliable evaluation of model performance. Cross-validation involves partitioning the data into subsets, training the model on some subsets, and validating it on others. This technique mitigates the risk of overfitting, providing a more robust estimate of the model's performance on unseen data. K-fold cross-validation, a popular variant, involves dividing the data into K subsets and performing K experiments, each time using a different subset as the validation set. This approach ensures that every instance of the dataset is used for both training and validation, enhancing the reliability of the evaluation. Real-world applications necessitate the combination of these theoretical principles with domain knowledge to select the most appropriate evaluation metrics. In a financial context, for instance, precision might be prioritized over recall to ensure that flagged transactions are indeed fraudulent, minimizing the cost of false alarms. Conversely, in healthcare, recall might take precedence to ensure that no potential cases of a disease are missed. These decisions are inherently tied to the cost-benefit analysis relevant to the specific application domain. The integration of these metrics into a comprehensive evaluation framework is facilitated by modern machine learning platforms such as TensorFlow and PyTorch. These platforms provide built-in functions for metric computation, streamlining the evaluation process. TensorFlow's tf.metrics module, for instance, offers a suite of functions for computing common metrics, while PyTorch's TorchMetrics library provides similar capabilities. Implementing these frameworks involves defining the model, compiling it with the desired metrics, and evaluating it on the test data. In conclusion, the theoretical basis of model evaluation metrics is a cornerstone of AI performance optimization. By understanding the principles behind these metrics, AI professionals can make informed decisions about model selection and tuning, ensuring that models align with the specific objectives and constraints of their applications. Practical tools and frameworks, such as scikit-learn, TensorFlow, and PyTorch, provide the necessary functionality to implement these insights effectively. Through case studies and real-world examples, the application of these principles becomes tangible, enhancing proficiency in optimizing AI performance.